So if you're an AI developer, you know this struggle, right? You've got the beautiful simplicity of Python on one side and the raw, face-melting speed of low-level GPU code on the other. But what if you didn't have to choose? What if you could have both? Well, today we're diving into Triton, the language and compiler from OpenAI that promises to do exactly that, to unlock peak GPU performance without making you tear your hair out. Okay, so here's our game plan. We're going to start by laying out the exact problem Triton was designed to fix. Then, of course, we'll introduce Triton itself, pop the hood to see how it really works, and then get into the nitty-gritty of actually developing and debugging with it. From there, we'll zoom out to see how Triton is scaling up in a huge way, and we'll wrap it all up with a big question about the future of AI. Let's do it. All right, first things first, let's talk about the central challenge in AI development today. It really is a classic dilemma. One that forces a really tough choice between making things easy and making things fast. So in one corner, you've got Python. It's where ideas happen, right? It's flexible, it's expressive, it's the language of AI research. But it was never built for the massive parallelism that makes GPUs sing. And then, in the other corner, you have CUDA. This is the key that unlocks every single drop of performance from an NVIDIA TPU. It is insanely fast, but it is also insanely difficult to write. You need a PhD-level understanding of the hardware to really master it. And that gap between the two, it's huge. And that is exactly where Triton makes its entrance. It was built from the ground up to be the bridge across that chasm, aiming to finally solve this tug-of-war between performance and productivity. So what even is Triton? At its core, it's a programming language that looks and feels just like Python, but it's designed to be compiled down into super efficient GPU kernels. The whole mission here is to give you that amazing developer-friendly vibe of a high-level language, but with the kind of performance you thought you could only get by painstakingly writing low-level code. And look, this isn't just some marketing fluff. It's a real, tangible promise. OpenAI is saying that with Triton, even if you've never touched CUDA in your life, you can write custom GPU code that performs like an expert wrote it. And sometimes you can do it in just 25 lines of code. That just completely lowers the barrier to entry for high-performance computing.
And hey, the numbers don't lie. This chart here is absolutely key. It shows Triton-generated code going toe-to-toe with cuBLAS. That's NVIDIA's own hand-optimized gold standard library. What you really need to see here is that Triton isn't just getting close, it's right there, hitting over 90% of the hardware's peak performance. It's delivering on the promise.
So, the big question is, how on earth does Triton pull this off? Well, the secret sauce, really, is all in the compiler. So let's go under the hood and see how your friendly Python code gets turned into a beast of a GPU kernel. Okay, this journey from your nice, clean Python code down to the bare metal is a whole process. It all starts with your high-level Triton code. First, that gets turned into Triton's own special intermediate representation, or IR. Then it gets lowered into a hardware-aware version of that IR, and this is where the GPU-specific magic starts to happen. After that, it's translated into the more generic LLVM IR, before, finally, being compiled into the actual machine code that the GPU can run. Now, the one concept you absolutely have to grasp to understand Triton is the tile. Forget thinking about individual threads or memory addresses. In Triton, you think in terms of these small blocks of data. By telling the compiler you want to perform operations on these tiles, you're giving it a much bigger picture of what you're trying to do. And that lets it make all these powerful automatic optimizations that would be a total headache to do by hand. And this image, wow, it just shows the difference perfectly. On the left, that's the old way, the CUDA model. You, the developer, have to manage this complicated grid of threads. But on the right, that's Triton. From your perspective, it's single-threaded. You just write one program that works on these tiles, and the compiler automatically figures out how to spread that work across all the GPU cores. It is just a massive simplification. And because the compiler's thinking in these tiles, it can pull off some seriously incredible tricks for you. It automatically handles tiling to fit the GPU's memory structure perfectly. It coalesces memory access to make sure you're reading from DRAM as efficiently as possible. It knows when to use that super fast on-chip shared memory, and it even prefetches data to hide latency. I mean, these are the exact kinds of pro-level moves that would take a CUDA expert weeks to perfect. And Triton just does it for you. All right, that all sounds great in theory, but you and I both know what happens next, right? Your perfect, brilliant kernel has a bug. So that brings us to the really practical side of things. How do you actually build and debug stuff with Triton? It's the question we all face, right? What happens when it breaks? And thankfully, Triton actually comes with a really powerful toolkit for when things inevitably go sideways. So you've basically got two lines of defense for debugging. First, at compile time, you can use things like static print and static assert. These let you check the shapes and properties of your data before you even generate any GPU code. Then, for when your code is actually running on the hardware, you've got device print and device assert to peek at the actual values and see what's going on. But okay, for the real hackers out there, this is where it gets fun. There's this amazing toolkit of environment variables. You can flip a switch to run your kernel on the CPU with NumPy, which means you can use normal Python debuggers like PDB. You can tell it to dump the intermediate code at every single stage of compilation to see exactly what the compiler is doing. You can even have it print out what the auto-tuner decided was the fastest configuration. It gives you this incredible level of transparency. Okay, so up until now, we've been talking about making one kernel on one GPU go really, really fast. But let's be real, the world of AI is way bigger than that now. So let's zoom out and see how Triton is evolving to power these massive distributed AI systems that run on supercomputers. Yeah, don't get it twisted. As models have gotten just gigantic, the whole game has changed. This isn't just about optimizing a single operation anymore. It's about orchestrating these incredibly complex workflows across huge clusters of machines. And a perfect example of this in the wild comes from ByteDance. They've actually built an extension they call Triton Distributed. It's designed specifically to make programming these huge systems easier by building communication right into the compiler itself. And the results? I mean, they're just staggering. By using this to perfectly overlap the computation with the communication across their entire cluster, their internal systems have saved millions of GPU hours. That's real money, real time, and a huge boost to their development speed. You want a mic drop number? Here it is. On some really tough, communication-heavy jobs, like you'd find in a mixture of experts model, the code generated by Triton Distributed was almost 45 times faster than the standard PyTorch setup. 45 times. That's not just an improvement, that's a complete game changer. And you know, this whole expansion isn't just about getting bigger. It's about playing nice with others, too. We're talking hardware. Triton was born on NVIDIA GPUs for sure, but now it has official support for AMD GPUs. The compiler is smart enough to have specific optimizations for both, targeting NVIDIA's Tensor cores on one side and AMD's MFMA matrix cores on the other. That makes Triton a truly portable, high-performance language. So, let's recap. We've seen how Triton builds that bridge between easy-to-write code and super-fast performance. We've looked at the compiler magic that makes it all happen, and we've seen how it's scaling up for the age of massive AI. And all of this leads us to one final, really interesting thought about what this all means for the future. You know, for the longest time, the gospel in this field was that if you wanted real, top-tier, peak performance, you had to get your hands dirty with something like CUDA. There was just no other way. But tools like Triton are seriously challenging that idea. They raise the level of abstraction so a smart compiler can worry about the messy hardware details. So it leaves us with this huge, fascinating question. Are we headed for a future where the world's most advanced, highest performance AI code isn't written by hardware experts in C++, but by algorithm developers in Python? It's a pretty wild possibility to think about.